Alrighty. How we doing?
Good, and you?
I'm good, thanks. My computer ran updates last night, so I've been working on getting everything pulled back up to the way I like to have it. And I just realized I didn't actually pull up today's lecture yet. Okay, good deal. Well, let's see, who are we missing? Okay, Emma's bag is here. We're missing a couple folks down there, Genesis and okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Down a few folks, but that's all right. They'll catch up. Alrighty. Let's see. Announcements. This is the last lecture of Module 2. So today is going to be, I got your thing in the mail, by the way.
Oh.
Beautiful pictures.
Did you like it?
I liked it, yes. Yes. Announcements, that's what I was talking about. Today is the last lecture of Module 2, which means that we are also having our exam to review today because I want you to have the weekend to prepare for and to take the exam, okay? So that by Monday we can start Module 3. Sound good? Because we only have 2 weeks left after today, right? I know. Isn't that crazy? Isn't that crazy? Is it 3 weeks? Is this week 5? Yes. No, definitely not week 4. We're past halfway. No, we are absolutely past halfway. Because in 2 weeks from today will be the 30th. And then the week after that is graduation.
We have 2 weeks in this class until graduation.
Yeah, 2 weeks after today. So this is the end of week 6.
That third week, we have our graduation on the Saturday.
Right, okay, no, you're right. Because week 8 is technically also graduation week, right?
Yeah.
Yeah. Good times. Had by all. Sarcasm. What was I saying? So besides that, yeah, I think that's all I've got as far as announcements go. So, any questions, thoughts, interesting things you saw / heard? I really enjoyed that out of nowhere thunderstorm we had yesterday. That was really cool. I love. If we could have that every day here, I would be a happy man.
The one we weren't here for?
I was here for it.
Seniors weren't. We were in Lubbock.
All right, you guys went on that trip. How'd it go?
It went good.
Nah.
Exhausted.
And is anyone genuinely planning on going there? Because it was Texas Tech, right?
No, it was Christian University.
Oh, okay. But no one's planning to go there? Don't you guys also do a Texas Tech trip?
No.
I could have sworn students have asked me about a Texas Tech trip before. Maybe I was wrong. Okay. Well, that's cool. Did you enjoy a road trip at least? Do you guys like road trips?
It was okay.
Yeah. Longest road trips I have ever been on. Back when we lived on the East Coast, I lived in Maryland, Massachusetts, Virginia, around those areas for about 8 years of my childhood. But all our family lived in California, and it was really expensive to fly a family of 8. I was the oldest of 6 kids. It was really expensive to fly a family of 8 across the country. My dad was a naval officer. They don't make a fortune, right? The military doesn't pay bank. So we would just road trip from the East Coast to California once every other year or so. So they ended up being about 36-hour road trips where my parents would go on and off, and we would go through the night and listen to my mom read us books. That's how I heard Harry Potter for the first time. Actually, technically hearing Harry Potter for the first time was on a road trip in Japan. We went from the bottom of Honshu up to the top near Hokkaido. That was about a day's worth of trip, but that's where she first read us Harry Potter. But Harry Potter was always a favorite, and Fablehaven and all sorts of cool books. It's where I got my deep love of literature, I think, was on those road trips. My mom would read to me. Where was I going with that? Oh, road trips. Yeah, you guys went on that trip. Cool. Let's see. Should we start off with something interesting? You guys know what I'm all about, right? With my research and my dissertation is all about lunar resources and things like that. Well, last week, Russia started making some public changes to the ways that they will be carrying out their space program. Now, Russia has always been our longest standing competitor in space and ally in space, interestingly enough. Not our longest standing ally in space, but a long standing ally in space, but definitely the longest standing competitor. Forever, it's always been Russia and the United States that have the ability to go to space, and other people kind of hitch a ride with us. China's been doing their stuff recently, right? And they're spending a ton of money to try and catch up. Do you guys know that China has their own space station? They can't operate on the International Space Station, so they built their own. There are laws. There's this thing in the United States called the Wolf Amendment that was instituted in 2011, which prevents the United States or any of its allies from participating in any Chinese endeavors having to do with space technology or space travel. And it's because of the extreme ideological differences between the way that China and the United States does things. For example, we have fundamental aspects of human life here that are embedded in our Constitution. The most basic, foundational document of our nation. All men are created equal is not something considered to be true in China. That's, a Declaration of Independence thing, right? As well. It's a concept that's in both. But then there are things like the Bill of Rights. Everyone has right to free speech. Everyone has the right to all of these things, right? They do not believe in those things in China. Someone starts speaking out against the government, they are immediately quashed, okay? China has a philosophy of the state controls everything, really. Private industry is almost always at least overwatched by the state. A big part of the reason why we've been able to springboard so quickly back into space after decades of not doing anything is because the United States government outsourced a lot of the productivity to private companies to invest in, like SpaceX and Blue Sky and a whole bunch, Blue Origin, okay, to do a whole bunch of stuff that NASA couldn't afford the time or money to spend time or money on, right? So China has not done that. As a matter of fact, they've only recently started attempting that. And that's why they have not been able to quite keep up with us yet. But the quantity of money they're throwing at it means that they are starting to catch up. Where was I going with that? Okay, but Russia has always been our most upfront, closest competitor when it comes to all things space. No more. Over the last couple of weeks, they have been restructuring their financial support of space. And I think it's probably, at least in part, in response to the success of the Artemis II program, right? Where we actually sent men back to the moon again. People back to the moon. Actually, I can't just say men, right? There was a woman on there, right? Where we sent people back to the moon, okay? They have basically, so they have this program, their actual program of going to the moon is called the Luna program. Luna 25, which they launched in 2023, crashed into the moon. There was a technological error, and it slammed into the surface of the moon instead of landing on it, creating a 60-foot crater because of the power of the explosion, okay? Ever since then, they haven't made much headway, and as of last week, they have delayed the Luna 26 and 27 missions all the way back for about 10 years. They have announced that they are reprioritizing their investments into space into military surveillance technology and updating old Cold War era technology. Which means that Russia has basically said, congrats guys, you got back to the moon first again. They basically are giving up on going to the moon. I'm not going to say they just handed it to us. That's basically what just happened. They are trying to reinvest on securing their space assets here instead, which, I'm sure that they will have a very strong Earth-based space satellite system, and we'll need to keep an eye on that for various, military reasons. But they are pulling back from any efforts to get to the moon, which means that at this point, as of this week, our only main competitor for the moon is China. One down. Now, I don't want that to sound like one down, one to go. I'm not campaigning for that. I think that we can very, very easily share space with China. But because of things like the Wolf Amendment, we cannot cooperate with them, which means it's a little complicated. Okay. Another thing to consider is our allies thus far in the space program are things like the European Union, the European Space Agency, the European Space Program, right? All of that. With Russia no longer a main player and China playing catch up to the US, it kind of, there's been, our pond just got a little emptier. So is the European Union going to simply be satisfied with being partners with us? I don't know. We've burned them quite a lot in the last couple of decades. We have pulled out of so many joint programs that we've been doing with the European Space Agency, including things like Gateway, which they have already invested a ton of money into. And then a couple weeks ago when we did that big exciting announcement, when NASA did that big exciting announcement about going back to the moon and going to Mars and nuclear technology in space, part of what they said was we are also not investing in the Gateway program for now. Well, that was something we were doing jointly with the European Space Agency. And they're like, what does that mean? Okay, can we even afford to do this now if the United States isn't involved? So they've kind of had to pivot because we don't tell them these things before we make public announcements, I guess. So I don't know. Are they going to be satisfied being the junior partner to the United States anymore? Or do they want to try and fill that niche? Niche left behind by Russia as a competitor going to the moon? Don't know. European Space Agency has, I want to say, 27 nations in it, all of which collectively have very substantial financial input. And they already have a pretty cool system where it's kind of a however much you put in is the benefit you get out of it, right? So Germany and France are like I want to say Germany and France are the two biggest donators, right? The financial supporters of the European Space Agency. They will, whenever there is like resources or any other positive thing that comes out of going to the moon, they will be the ones that get the most out of it. However much you put in is how much you get out, right? Proportionally speaking. Which is a very good system to have between a whole bunch of small participants, I think. And probably, at least my argument is, a pretty good baseline to work with as far as sharing things in general on the moon. But I think that my argument for my dissertation just got a little harder because Russia is not a major player. What? How we share the resources on the moon and how we do it responsibly so that we don't run out before.
So how does it get harder? Would it make it easier? Or why does it essentially get harder?
It's a great question. Why does it get harder? Do you know what a Mexican standoff is?
Yes, I think.
But then,
Yeah.
Yeah.
I got my 2 guns on 2 people, and each of them has their 2 guns on 2 other people, right? You have to keep an eye on both people here. It's dangerous, but you also know that guy is just as likely to kill that guy as he is to kill you. If it's just a normal standoff, it's just me and you, baby. And the first guy that blinks, that's it. There is no third party to keep us in check or for me to keep my eye on. I don't keep doing this. I got this. We're far less likely to cooperate that way. Especially given the depth of the valley of ideology between us and China. Something that would cause the Wolf Amendment to be made in the first place. Their labor laws, like the quantity of child labor that happens in China, is something that is unconscionable to happen in the United States. And anytime we find that happening in the United States, people go to prison. But that's a state-sponsored act over there, right? They encourage it. Anybody that is able to work does. This is why China is such an incredible economic powerhouse. They literally will put anyone to work. And it's a philosophy that has taken them very far as a nation because they are incredibly wealthy. They have an incredible number of resources that they can and do go for it. They also are not as environmentally conscious as we are. They will strip rainforests. They will dig up coal. Right now, they are burning more coal than any other nation in the world. Now, granted, a lot of that energy is going into making sustainable energy sources. They are investing into nuclear. They are investing a lot into solar and geothermal and stuff like that with that energy, but they are also producing more greenhouse gases than anyone else in the world, too, as a result of burning all that coal. So we just, ideologically, the United States and China are not simpatico, even though we are economically reliant on each other. So that's why we can't cooperate with them, which means that it's not as simple as, hey, let's run on over to Beijing and set up some sort of treaty with them. We are literally not even allowed to do that. We cannot cooperate with them on space-based activities, which means that as of right now, we cannot be anything except competitors on the lunar surface. I am holding out hope that that will change in the future because I'd love to cooperate with them at some point, but at the same time, there's a part of my conscience that says, yeah, but there are 7-year-olds working in factories, you know? Anyways. Yeah, so things in my neck of the woods got a little more interesting this week. I'm kind of shifting my dissertation to be less of an international treaty system and more of an intercorporate treaty system, because now that Russia and Russian companies aren't going to be directly investing in the lunar surface, a lot more American companies will be able to cooperate to work up there together. So that's what I'm going to be kind of shifting my focus towards, trying to make sure that people that have American bases, you all right? Aren't gonna, where's your tail? You're kind of like, come here. Yeah, that'll work. Okay. Yeah, okay, so that's that. Questions or thoughts on that? Appreciate the questions. Are you cold? A little bit? Wish I could change the temperature. Can't. Okay. All right. Okay. We're going to talk about evolution in the fossil record today. Like I said, this is the last part of Module 2. So we've already talked a lot about evolution. We actually talked about the mechanisms for evolution. What are some of the mechanisms of evolution we talked about?
Mutation.
Yes, what is mutation? Something with genes and DNA? Well, we haven't quite gotten to genes yet. We will be talking about genes today. Do you already have an understanding of what genes are?
It's what gets passed down.
Okay. Something gets passed down from one generation to another. If that weren't true, you wouldn't have your mom's eyes. Do you have your mom's eyes or your dad's eyes?
They have the same.
They have the same eyes? Oh, okay. So I would have been right anyway. Great. Okay. So we will talk about genes today and what that is and what that means. What are some other mechanisms of evolution? We talked about mutation. What causes mutation? Radiation. Radiation doing what? Yeah, it messes with the DNA, changes things. Do mutations have cause or purpose? Do mutations happen intentionally for a reason? I suppose if you are particularly religious, you might argue that mutations do happen for a cause or a purpose. But with our current scientific understanding, no, mutations are completely random. Now, like I mentioned before, I am not in any way attempting to argue with the concept of a God or creation. I have my own personal views on it, but I'm not going to argue with anyone else's. If you want to have that sort of conversation, I am happy to have that outside of this class recording, because this goes on YouTube. I'm not going to put that sort of conversation on YouTube. Heaven help us all, right? The sort of firestorm that would make. Yeah, happy to have those conversations outside of class time. But what we understand about mutation is that it is completely and utterly random. A lone proton blasting its way through space makes it through our atmosphere and flicks that little amino acid off, changing one aspect of your DNA, which is the code for how your body behaves and grows. And if it does that to your DNA, and then that DNA gets passed on to your offspring, guess what? Your child is going to have some sort of mutation as a result of that. Now, this is an important concept that I didn't really spend much time on in the past, but we are definitely talking about today. What does that mean as far as mutations for you? If I bombard myself with gamma rays, am I going to become the Hulk? I am. Ivan says yes. Why didn't I just do that instead of getting a career? Well, it is extremely dangerous because no, you would not become the Hulk. Here's the key thing. Mutations don't actually change things about the way that your body functions, except negatively. Because a mutation in your DNA is going to cause your body to behave or grow in a way other than it was programmed to do initially. A mutation in DNA that gets passed on to your offspring grows with that mutation. It is a part of their original coding. Your body does not do well, just like a computer does not do well, when alternative programming comes in. What do we call it when an alternative program starts trying to take over a computer's function? That's a computer virus. And it makes your computer crash or start screaming like a jet engine, right? Because it's trying to reconcile different types of functions, okay, all at the same time. So, when you absorb radiation, your body suffers some negative effect. Well, minor amounts of radiation, we call that a sunburn, right? But what about massive doses of radiation? That'll give you cancer. Or straight up melt you, like what we saw happen in Hiroshima and Nagasaki after the nuclear bombs were dropped. That was only a small dose of how much potential those bombs had. If I told you about the potential in those bombs, yeah, I told you about that. Only 0.1% of the uranium actually went up in that explosion in those bombs. Could have been far, far, far worse. Yeah, okay, so that's the concept of mutation. We cannot give ourselves superpowers for that reason. There's another reason, which I will get to later today, for why we cannot simply give ourselves superpowers, okay? But I want to start off today by talking about this guy named Charles Darwin. Have you guys met Charles Darwin? Have you heard of Charles Darwin? Yeah, he is widely, what's the word I'm looking for? He has been kind of given the title of the father of evolution. He was not the only person to work on it, though. There were lots of other people who had similar ideas, and all of those ideas combined with Darwin's kind of came together to make our modern theory of evolution. Not everything that Darwin got right, or not everything that Darwin said was right, as we understand it now. But most of his stuff, in combination with the other things that people in his time period were working on, are what go into our theory of evolution. Fathers of science are they're tricky things. We often put people up on pedestals and forget that they were human. Have you guys ever heard the name Louis Pasteur? Huh? Louis Pasteur. Whenever you go and you get your milk at the grocery store, or you get your sour cream, or any dairy product, it's going to say the word pasteurized on it, right? Pasteurized. Do you know how you pasteurize a milk product? Do you know why you pasteurize a milk product? Milk products come from living bodies, cows, goats, things like that. Yes, full of the bacteria inside of those organisms too. And other bacteria love to eat that lactose-based stuff. How do you kill all that? Because if you eat it, you get sick, right? How do you kill the bacteria in it? Pasteurize it. How do you pasteurize it? With heat. Yeah, you heat it up and it kills the bacteria. Here's the thing. You mean you kill off some of the good bacteria too, but you got to pick your battles, right? That's why you'll find milk products that are what they call probiotic. They've had friendly bacteria re-injected into it. Okay? Now, here's the thing with Louis Pasteur. Forever, hundreds of years after the discovery of the process of pasteurization, he's been held up here as one of the pinnacles of scientific discovery. Let me tell you a little bit about this. There was a guy named Tresson around at the same time as Pasteur. Can you tell these guys were French?
Yeah.
Okay, yeah. Jean-Joseph Tresson, okay, was this guy's name. Now, he theorized that you could remove they didn't call them bacteria back then. What do they call it? They had a special name for it. They didn't know what was in the stuff, but they knew that something was making people sick. And these people were theorizing. I forgot what the name they had for what we call bacteria now. They've called stuff that makes you sick lots of different things over time. Negative humors, bad things like that, okay? But now, we call them bacteria, so we'll just call them bacteria. They theorized, Tresson theorized that you could remove the bacteria by heating up the substance. Okay. Pasteur ridiculed him publicly. Said, that can't be it. Oxygen treatment. So he demonstrated this by taking sheep and injecting them with the anthrax virus. Okay? This was his attempt to prove that his process of pasteurization could work for what we now call vaccines. Vaccine is something that you get that prevents you from getting sick or lessens the effect of something that can get you sick, right? Vaccines are kind of a hot topic in our society today, but this is where the concept of a vaccine began. They were trying to inoculate or stop people from getting sick before they ever got sick. Anthrax was a problem at that time. We don't have anthrax anymore. Yes? Say that again, I'm sorry. Oh, what they called the bacteria? Yeah. Animalculus? Could be. I mean, you're probably right. I just didn't remember what the name was. You're probably right. What is it? Yeah. Animalculus? Yeah. Sure, that's what they called them then. Okay, thank you for looking that up. So he injected these sheep, half of the sheep, with his vaccine that was oxygen treated. Okay, a strain of the anthrax virus that was oxygen treated instead of heat treated. And then he left them out in public, and the half that didn't get vaccinated died, and the half that did get vaccinated lived. Yay! Pasteur's a genius. Until recently, people started going through his notes. I say recently, I say 100 years later, which is like 100 years ago now, something like that. Okay, but they went through his notes, and they found that he lied. He realized early on that his oxygen treatment technique was not going to work. So he used Tresson's heat treatment technique to make his viruses and then told people it was his discovery. Tresson died a pauper in a gutter, while Pasteur became a hero of medicine and richer than sin off of lying about which process he had used. And now we have, it's so-called the pasteurization process, the application of applying heat, even though it was Tresson's idea that Pasteur took. By the way, he did the same thing with the rabies vaccine. There was a guy named Gautier who came up with a way of discovering the rabies vaccine. And Pasteur did the same thing. He took Gautier's ideas, discredited him publicly so no one would listen to him when he said that they were his, and then experimented with the rabies vaccine on people, by the way. People who died, because he would give them the vaccine, which was not proven to work, and then get them sick with rabies. And then they would die from rabies until he figured out what the correct technique was. But he hid the dead people, so no one knew that this happened until way later on, and they went through his notes, right? So, yeah, it's like dark stuff, right? So my point here is, science has come a long way, and it's not always been clean. The fathers of science, as we call them, and by the way, plenty of mothers of science, I mentioned them last time we talked, right? Marie Thorpe and Mary Anning and so on and so forth. Take discoveries with a grain of salt, because we may find later on that they weren't quite as correct as we thought they were. For a long time, people thought that continental drift was the thing. Now we know it's plate tectonics, right? So this is just my caution. Grain of salt, critical thinking required, okay? Something I'm trying to really push home here. All right, so now let's talk about Darwin. Darwin was a naturalist, which again is someone who kind of has their fingers equally in every scientific pot, physics, chemistry, biology, geology, all of that, okay? He tended to lean a little bit more towards biology, but he was well-versed in all of it, okay? He went on a voyage on this ship called the HMS Beagle, okay? The Beagle went across the ocean, actually visited a lot of different places. But the one place that I'm going to mention, two places technically that I'm going to mention on his voyages, he speculated a lot on observations he made of South American creatures and creatures that lived on islands, specifically islands in a chain called the Galapagos. Okay, let's talk about South America first. He started asking questions like, okay, we observe these animals in South America, these animals in North America. There are similarities between ones in the North and South America. Cool. There are no similarities between the animals in the Americas and the animals over here. But then there are other animals in Africa that resemble animals in South America. And he started trying to put all these puzzle pieces together, and it wasn't working with the current understanding of the distribution of continents and where life came from. There were things that weren't adding up. And what's the most important place to start in science? With a question. So he started asking all these questions and trying to find answers for them. Okay. Then he got to the Galapagos. The Galapagos Islands are freaking cool. I want to go there sometime. They are extremely protected. Okay, one of the places on Earth that has generally accepted international protection laws. Okay, because they are a natural reserve, primarily based on the observations he made there. Okay, he observed how wonderfully unique the organisms there were, and how you could make interpretations of those organisms, the differences and likenesses between those organisms, to come up with a theory that would eventually become evolution. Okay, so what did he find? Well, he went to the Galapagos Islands, which is a whole bunch of islands. I think I have a map. Yeah, these are a few of the Galapagos Islands right here. That's only a few of them, okay? But there's some distance between them. But on each of these islands, there are finches. Do you know what finches are? It's a type of bird. Yeah. It's a type of bird that we'll find in pretty much every major continent. I think most continents have some kind of finch. They're pretty well spread out. But I don't know if that's actually true. I know that they're in a lot of places, but I don't know if they're on every continent. But regardless, there's a population of finches on this island, and the reason why, we believe, is because at some point a population of them got blown to that island in a storm. Okay, great. So X number of years ago, a population of finches arrives on the islands. Fantastic. But the finches on every island are slightly different. Some have small beaks, some have big beaks. Some are large bodied, some are small bodied. Some have big eyes, some have small eyes. They're clearly all finches. But why would they have such different traits from each other while being so geographically close to each other? What do you think?
It would be the evolution, right? Because they use their beaks for different beaks.
Huh? Oh, okay. I want to start with that comment, and then we'll come back to yours, okay? The environment. What would the environment do? These are all aspects of the environment, the type of trees they live in, the landscape, the geography, the type of food that's available. These are all environmental factors. But do environmental factors decide evolutionary changes? No. Predators are an aspect of the zoo. The environment does not decide anything. It sets a bar. And if organisms can't measure up to the bar, they die. How do organisms change to measure up to the bar? Natural selection is something we're going to talk about in a minute. We haven't got there yet. Mutations causing changes in the DNA. Those changes result in new traits. Those new traits will either be positive or negative in the environment. Positive traits get passed generation to generation. Negative traits mostly don't. Why? Because the organisms that evolve or that mutate negative traits don't live long enough to breed. So which means that, in general, only positive traits get passed generation to generation.
Has there been any organism that has passed down negative traits because they managed to breed quickly?
Yeah. Can you guys think of an organism on our world right now that has passed on negative traits because they breed? Nature doesn't weed it out. You're looking at it. Us. We control our own evolutionary path now. What do I mean by that? In nature, if I evolved a trait that was negative, like, say, poor eyesight, I'd die pretty quick. In human civilization, having poor eyesight doesn't matter a lick. We've developed technology, and we have social empathy. Even if we didn't have technology to make my eyesight better, people would take care of me. We see it every day. How many of you wear glasses or contacts? I have contacts on right now. My eyesight is so bad that anything that far from my face is a fuzzy blur. If I didn't have my contacts in, I wouldn't be able to make out any one of you different from the rest of the surroundings. You would all be fuzzy blurs. That does not survive in an environment outside of human civilization. But because of human civilization, negative traits get passed on. Great question. Now, I'm going to take this another step forward, and I hope you don't think less of me for it. There have been people in our world, every now and then we'll get someone like this who somehow makes it into a powerful position and then gives the rest of humanity a hard time for it, who think that negative traits should not be passed on to the next generation. Do you know what this concept is called? Eugenics. Some very well-known eugenicists, Mao in China, Hitler in Germany, who believed that their particular race was the perfect race, the pinnacle of creation, and no other race could measure up, and therefore needed to be either subjugated or destroyed. And whenever these people make it to power, the rest of the world suffers for it. Millions of people die as part of this fight to purify the human race. So, what's their philosophy? Only the best parts of humanity should be moving forward generation to generation. But who decides what the best parts of humanity are, guys? One guy who wears a funny hat and does a funny salute and has a tiny mustache? That's not right. So what's the solution? We don't do that. We don't say only these traits are worth saving. Every human life has value, priceless value, which is why we will spend hundreds of millions of dollars to rescue one astronaut in space or one person stuck at the bottom of the ocean, right? We have laws in place to save human life for this reason, okay? Because civilized society does not hold to eugenist values, okay? But here's the other side of that equation. What would life be like? By the way, I am by no means a eugenicist, but I do point this out because I'm a scientist and it's worth to look at both sides here. Some common traits that we see passed on genetically: autism, Asperger's, genetic cancer. These things are becoming more and more common in our society because they are negative traits that are not naturally weeded out. Okay? The rate of these things appearing in bloodlines is increasing. I'm not saying we will ever reach a point where it is epidemic in society. It is simply a fact that it is becoming more and more common to see generation by generation, because people with those traits are able in our wonderful, beautiful, loving, empathetic society to pass those traits on through breeding. Okay? I personally am the excited beneficiary of genetic skin cancer. Every male in my mother's side, it skips a generation, as many genetic traits do. They become recessive and then dominant through generations. Okay? Something we'll talk about when we talk about genes. Every male on my mother's side has died of skin cancer every other generation. Last one being my grandfather, making me the next person in line. Now, in a society that does not preserve someone who has those traits, I would never have been born. Because my grandfather or my great-grandfather or my great-great-grandfather, whoever else further along the line who got assistance to survive that, at least long enough to have children, would not have survived, and therefore I wouldn't have it, but I also wouldn't have been born. So here's the quandary. By saving those aspects in society, we have more people. Those people get to live lives and contribute to society, but those traits continue to pass on. Yes. Yes, Fiernan has something to offer to this discussion. Man, he's loud. I'll feed you after class. Gosh, I fed him yesterday. What a greedy Gus. You only have to feed these frogs once every 2 or 3 days typically, but they are greedy. Anyways, yes, so that's a viewpoint worth thinking about, right? And again, I'm not saying eliminate all of those things, but it is worth noting. Okay? Interesting. Okay, so back to our finches, though. The finches have different traits. Small beaks, large beaks. Why would you have different sizes of beak? What environmental factor could control that? What about your food?
I'm guessing the bigger beak eats nuts.
Yeah, exactly. The bigger beak is meant for crushing nuts, berries, seeds, things like that. Smaller beak, look how aerodynamic that head is. Faster flight. Small, narrow, fast closing beak. Great for catching bugs out of the air. So, X number of years ago, a single flock of finches makes it to these islands. And over the years since, as the finches spread island to island, maybe one island has less seeds but way more flying insects. One island has less trees, more bushes. One island has more wind because it's exposed to the trade winds, and another smaller island is behind that and therefore protected by the wind, right? So you have all these different environmental factors within which each of these populations of finches has adapted. And how does that adaptation happen? Random mutations, some of which are successful and spread through the population. This is an actual, quantifiable proof of the concept. Okay? Another example, tortoises. These guys, boom, boom, boom. All of those. There are Galapagos tortoises on pretty much all of those islands. They each have different shell structures. They hold their necks at different angles. They look a little different from each other, again, based on environmental parameters. By the way, Galapagos tortoises, largest species of tortoise on the planet. Also the oldest living. They can get 5 to 6 feet long. Yeah, I've seen a Galapagos tortoise that I could sit on and ride like a horse.
Have you ever ridden it?
I mean, I saw it when I was 14, and it was at a zoo, so no. I've seen Galapagos tortoises since then, none that big though. It was a truly massive tortoise. They can also live to be about 200 years old. Yeah. The Galapagos tortoise, very long-lived. Primarily because of things like metabolism, okay? Slow-burning metabolism have added to that. There are quite a number of studies, actually, into why they're able to live so long. It's just like they have such a chill lifestyle. They don't do much. They wander around their islands and eat grass and roots and hang out in the sun and go to sleep, and they just chill. Huh? What's their natural predators on those islands? There aren't really any.
That's why they live so long. Right?
That's why they live so long.
Is there an overpopulation?
No.
What keeps it under?
Now, there was a period of time when people would go and eat them. Yeah, they are endangered. I think that they are still actually considered endangered. But yeah, turtle soup, unfortunate.
Have you ever tried turtle soup?
No. I've eaten a lot of things. I've eaten,
That's
close your ears, I've eaten frogs. I've eaten, close your ears, I've eaten snake. Now that I think about it, I think I've eaten at least one example of every animal I own. I've had lizards too. Oops.
That sounds like it would be good.
Lizard?
Yeah.
It is, depending on the type of lizard and how you prepare it.
What's your favorite type of lizard?
Gosh. What was the name? It was a lot of the more exotic dishes I've eaten are like Southeast Asian dishes. One Southeast Asian dish that I haven't eaten yet is scorpion. Thinking about,
Have you ever had
I
those
would.
scorpion popsicles?
no.
No.
No, I've had several of those candies that have the scorpions in them, but I haven't eaten them. I just keep them for novelty. Yeah, or I give them to my kids and watch them freak out. Like, it's candy. Don't you like candy? I have had a couple of very interesting dishes. Oh, dinuguan is actually, I like dinuguan. It's pork blood on rice. Oh yeah, I told you about that. Yeah. So I've told you about a lot of the food that I've eaten. It's pretty good. Okay, so back on topic, or else we're going to be on this forever. Okay, we're only on slide 2, guys, and we're an hour in. All right, so yes, the finches, the tortoise shells, all of these examples that he observed, which led to his publication of his book called On the Origin of Species, okay, which is where a lot of the theory of evolution is contained. Okay. Now again, we know a little bit more about it now. We can refine his ideas down a little better, but for the most part, he nailed it. He got a lot of things right that we've elaborated on since then. So now let's talk about this thing which he called natural selection. You brought this up. What is natural selection? What is your perception of natural selection, guys? What do you think of? Is there any choice?
Well, they always used to say survival of the fittest,
yeah,
but they always said like that was wrong.
Survival of the fittest. If survival of the fittest were true, then where do sheep come in? Sheep are dumb. I mean, there's an element at play here, which I'll talk about in a minute. All right, what about dodos? Dodos were super dumb. What about lemmings? Lemmings are super dumb. If survival of the fittest were a universal law, then why are all of these things, which clearly have very little capability to take care of themselves, where do they come from? They're still here. It can't be survival of the fittest, therefore. Fittest, by the way. What does that mean? Smartest, most dangerous. That's typically what that would mean. Survival of the fittest is not a universal law, therefore. Natural selection. Let's go back to that. What is natural selection? Cade, what do you think? Oh, sorry, Cole, not Cade. Oh, I have another Cade in another class. Cole, what do you think? So what you're saying is that, okay, so whatever the apex predator is, more or less has control over the selection of what survives? Not really. No, a great white shark could not care less what the minnows down at the bottom of the food chain would be doing, right? It's not actually right. Interesting thought, though. And there may be some tie-in for that for something we'll talk about in a little bit, and where humanity comes into play, where we consider ourselves the apex predator of the planet, and we do have some influences, but not what I'm looking for.
Natural selection of that what's the word? To be able to adapt.
Adaptation.
Yeah. This is that concept of adapt or die, right? Natural selection is essentially the weeding out of organisms that do not have successful, positive mutations in time. If our planet is undergoing climactic cooling, only the organisms that are capable of adapting fast enough will survive. Every time that our planet goes through a cooling or warming trend, yeah, we see a lot of things die off because they can't adapt in time. Adapt or die. Natural selection. Okay, so this preserves successful traits and eliminates the organisms that evolve negative traits. Nothing decides what a positive or negative trait is. There is simply a bar which is set by the environment, and only organisms that can develop traits to measure up to that bar survive. So then, artificial selection. What do you think that is?
Artificially, like selecting the traits, like you choose the traits, like the breed of dog.
Me?
Or human.
We need to be very careful with things like the word you or me or we, right? I am guilty of saying the word we a lot. Like, we usually represents scientists, or we can represent the United States. Elaborate. We, what do you mean?
As in, like, humans choose, like,
Humanity, okay, yeah.
like humanity chooses what they want. Like, what if they want like a smaller dog, so they breed for smaller dogs.
Yeah, exactly. Exactly.
They want a brown-eyed dog or multicolored.
We decide what a positive trait is or a negative trait. How did this begin? Dogs are a great example. Okay? Any domesticated animal or plant, we have done this to. But let's talk about dogs. Dogs are a completely fabricated, unnatural organism on our world. Why? Because we started off with wolves. Thousands of years ago, someone found a wolf pup. Decided, you know what? I like pets. Birds are getting old. My rat isn't as fun anymore, maybe, right? Whatever the reason was, I want to take that wolf pup and I want to raise it. Now, that wolf pup was probably pretty aggressive, and it probably had pretty coarse fur, and it probably had pretty big teeth, and it probably snapped at its master every now and then. Hard to tame a wolf. But given enough people doing that, hey, that guy's a wolf, I want a wolf. Helps him hunt, keeps him occupied, like companionship, keeps his kids, happy because they have, something around the fire, or they like feeding it or something, okay? So it protects his flocks, right? He's trained it to not, eat his own sheep. So other people start doing this. And then their wolves start breeding with each other. And eventually, you realize this wolf had brown fur, this wolf had black fur. Some of their offspring have brown, some of them have black, and some of them have a combination. That's the fundamentals of what would eventually become genetics later. They didn't call it that, though. They just knew that some things got passed down, which meant that they realized they could control what traits offspring would have. I want my wolf to have softer fur. So a wolf that has genetically mutated to have softer fur is preferred. And they preferentially breed that one and not the others. Okay, well now I have a population of wolves with softer fur. I want my wolf to be more docile. I don't want it to snap at me that much or bite off my kids' fingers. Oh, want, right? Okay, so they breed the wolves that are more naturally inclined to have sweeter temperaments, not aggressive temperaments. And one selection after another, humanity eventually ended up with where we are today. Hundreds of breeds of dogs. Chihuahuas and Great Danes are the same species, separated by thousands of years of artificial selection. Completely fabricated by us. By the way, this isn't just true of dogs. Pretty much every domesticated animal out there. Cows look nothing like their ancestors did. Sheep, pigs.
What are cows' ancestors?
Cows' ancestors actually came from Europe. Yes. So you know the North American bison? What do people usually call those? What's the other name that people have for those? Huh? Buffalo. Yeah. The North American bison is a bison, not a buffalo. The name buffalo actually came from an animal that used to live in Europe and is now extinct. The European buffalo was that animal's name. Very similar, about a cousin, you could say, to the Asian water buffalo. Looks similar to that. Those European buffaloes were the ancestors of the cows that got domesticated from the European buffalo populations. So they got domesticated in Europe and then brought to the United States. The native population of those that filled the same niche was the American bison. Yeah.
Why did cows start having these little bumps on them? Like the brat,
The what's?
like the brat, like they have a bump on
The bumps on the back?
Yeah.
I believe the bumps on the back are fat deposits. Yeah. Kind of similar to, I think, what camels do, where they keep hydrated fat on their back, and that's what the humps are. The more dehydrated a camel get, the smaller the humps get. Except I think that on a cow, those humps are just fat. I'm not sure, though. I'm not a cow expert. I like to eat them, though. Cows taste good. Right, okay, so any domesticated animal. By the way, do you have any idea how much of our planet we have domesticated? When you take into account every domesticated animal and every domesticated plant, which includes the crops that we have artificially selected traits for, disease-resistant wheat, roses that will resist certain species of insects, right? Or that no longer have thorns, thornless roses. Roses by default have thorns, but you can genetically alter them to not have thorns on them, okay? Every domesticated organism in our world makes up, what was the statistic I saw? 70-something% of the total biomass on our planet now. Most of the biomass on our planet has been artificially selected by us. How's that for an influence? By the way, every time we do this, we deviate from the natural course of evolution. Does evolution have a course to speak of? Not one that we know. Not one that we have any evidence for. It's random mutations that are successful or negative, dictated by the environment, the changes in the environment. There is no set course, but we have changed it by the actions we take and selectively breeding them. Interesting thought. Okay. Now, evolution, going about this process on its own, is going to eliminate some factors over time. For example, wisdom teeth. How many of you have wisdom teeth, or are they growing in? Do you know what wisdom teeth are? It's a set of molars that come in at the very back of your mouth, top and bottom. Okay? Do you know if you guys have any yet, or if they're coming in? A lot of you are at about the age when it would be. Chloe, do you have wisdom teeth? I had mine removed when I was 18. Okay? A lot of the time they will get removed because we don't need them anymore. We used to use them, an extra set of molars, for chewing uncooked grains and things like that. Our ancestors would eat things uncooked. And so we would need the extra teeth to grind them down so our intestines could process them better, right? But we don't need those anymore because we cook our food up, we process our food. It is no longer a positive mutation. When there is something that is in an organism that is no longer necessary, it is no longer needed, it becomes a positive mutation to remove it. And you know what? It's happening. I grew wisdom teeth. Chloe grew wisdom teeth. But every generation, more and more people are being born without the ability to grow wisdom teeth. It's fascinating. Last term, I kind of did a poll of the classroom to see how many people. There were 2 people in my classroom who had no wisdom teeth. They were old enough for them to start growing, and the dentist x-rayed them. There are no wisdom teeth. More people every generation, that's going to manifest. Why? It is no longer a positive trait to have them, and so the new positive trait is not having them. That's less energy and material your body has to put into growing something that you don't use. Same thing with an appendix. Do you guys know what an appendix is? Your appendix is your organ that produces enzymes to help break down tough-to-eat foods like raw meat. How many of you eat raw meat? No? No one likes a cannibal sandwich in here? You guys know what a cannibal sandwich is?
Yes, it's raw.
Yeah, you just take ground beef, you throw it on bread, right? It's gross.
Have you had it?
No, it's gross. I'll eat all of that. I mean, if it was part of an exotic dish, I probably would try it. I've eaten a lot of raw meat, but not raw hamburger, right? I don't think I would go that far unless it was part of a more exotic dish. But yeah, I know. We don't eat raw meat like that anymore, so we do not need our appendix, which is why they're becoming more and more of a problem. Lots of people will suffer from something called appendicitis. Appendicitis is when your appendix, being unused, is also unmaintained by your body, and the enzymes within it get kind of out of control, and your appendix can burst. Now, those enzymes, which are meant to break down raw meat, are not very friendly to your body. Appendicitis, if your appendix bursts, you will die unless you are immediately treated. Like, they need to open you up right away and clean that stuff out, or it will kill you. So, if you ever experience like an acute pain in your lower stomach, particularly over, I think it's on your left side, probably a good idea to get that checked. If it doesn't go away after 24 hours, if you can confirm, oh man, I don't just have gas, right? If it's way more painful than that and it doesn't go away, go get checked, because it is not worth waiting until your appendix bursts, because that's when things get real hairy, okay? Our body doesn't need that anymore, and there are people being born without an appendix now. Yeah, interesting. Do you know that snakes, some species of snakes, have legs? Yeah. Anacondas. We will sometimes find anacondas that have little nubby legs on them, like this. Some species will still use them for grasping each other during intercourse, but for the most part, they're gone on other species of snakes. But these snakes, they have tiny little leg bones inside of their bodies that manifest as these little nubbins on the outside. Why? Because snakes came from lizards, right? They have the same common ancestor. If you go and look at my skink in the zoo, I would bring him out here, except he would try to eat me, okay? Because he was wild. He still doesn't like being held. I've had him for like 6 months. He's gotten way calmer, but he still doesn't like being held. If you look at him, you'll notice he has a very long, smooth body, just like a snake. And then those 4 little legs, tiny little legs. If those legs weren't there, he would look just like a snake. He just has those tiny little legs, right? So, those legs have gone away over time, and just tiny little vestigial limbs remain. That's what we call these vestigial remains, okay? Things that are being weeded out, evolutionarily speaking, from a population. All right, so let me correct some misconceptions about evolution, by the way, okay? Evolution, if you want it in a nutshell, is a change of inherited traits over generations in populations. So here in this classroom, that's a bad example. If you take the state of Texas and you completely isolate it from every other state, some people want that, right? And completely isolate it from every other state, given enough time, the population of humans in Texas will slowly start deviating in appearance and function from the other humans in the rest of the world. Just like the finches in the Galapagos. Different physical characteristics, different ways of thinking, probably different technologies, but that's slightly different than evolution. Okay. Also, there is this misconception that evolution is the magical solution for how life started. It is not. There is nothing about the theory of evolution that goes against or for the existence of a God, for example. This is a very common misconception. Okay? All evolution does is explain how life changes over time. It in no way attempts to explain how life began. Okay? And it's important to note that evolution is not the magical solution for every biological change. For example, I was a baby. I am no longer a baby. My hair used to be black. Now it is slowly becoming more white. If any of you have gotten a close-up view of the right side of my head, you'll notice the quantity of white hairs I have there now. I fully expect I'll probably have the salt and pepper hair before I'm 40. Okay? These are not evolutionary changes. These are examples of what we call ontogenetic changes. Essentially, changes that happen to an individual over time, okay, as we age, as we get older. So obviously, there are changes that result in the change of an organism, okay? There are changes that are not in any way connected to evolution, okay? And then here's another important concept. Because these changes are happening as a result of random mutation to a DNA, you can't undo it. Evolution does not reverse itself. This is called Dollo's law. There is no function in our DNA or in our body that says, oh, that happened, let's fix it. Okay? The change is there. It is manifested. The mutation has occurred, positive or negative, whatever it is. Okay? Can't go backy. No takesy backsies, right? But you can experience another mutation that is similar to a previous one. The statistical likelihood of having two mutations that are exactly the same, not likely. For example, how many different types of flying things do we have in the world? Give me some examples. Birds, bees, bugs, okay? Bats. Can you give me something that doesn't start with a B, maybe? Birds, bugs, bees, bats.
Ants.
Today's letter is B, class.
Flying ants.
Flying ants, okay.
Bugs?
Yeah, that would be bugs.
You don't want me to-
Flying fish. They don't fly for long, but they do fly. They glide through the air for a little bit, right? Flying squirrels. Yeah. There are many actually, different ways that things have figured out how to fly. How many of them look the same? They might have similar traits, but does a bird wing look like a bat wing? No. Does a bee wing look like a flying fish fin? No. There are some things in common, but not the same thing. These are examples of how evolution can lead to similar situations. For example, it was beneficial for any of or all of those things to learn how to fly or to have a mutation to fly in the environment the way that it was. That's why it was a positive mutation that spread through the population. But none of them evolved the same way. None of them evolved the same characteristic. the statistical likelihood of the same evolutionary thing happening, it's like 1 in, what was it? 1 in 10 to the 25th. It's a lot of zeros, guys. So this answers one of our this actually addresses something that I mentioned before. Feathers on dinosaurs. Why all of a sudden are dinosaur toys and dinosaur pictures showing a lot of feathers on them? Because we found feathered dinosaurs in the Jurassic. If there were feathered dinosaurs in the Jurassic, and there are feathered dinosaurs now, aka birds, dinosaurs in the middle would have had feathers. Because the statistical likelihood of feathers evolving twice, infinitesimal. Therefore, logically, according to Dollo's law, as we understand it, dinosaurs in between must have had those feathers. And now we have found fossils since then to confirm it.
So what's an example of like getting a similar trait again?
Bird wings and bat wings both allow those organisms to fly, but they are not the same evolutionary mutation, right? In the case of a bird, they developed wings that were long enough to sustain them in flight. In the case of a bat, it's an extension of the skin between fingers. Like the skin that we have here, imagine if you developed a mutation that caused that skin to expand upward between your fingers. That's essentially what happened to make bat wings. Different mutations that lead to the same result of flight. Okay? Okay. This is an armadillo. How many of you guys have seen these dead on the road? Oh, you got to go up north. Go up north or out east, and you'll see these all over the place, dead on the side of the road. South, too, actually. We live in a surprising little pocket where there aren't a whole lot of armadillos dead on the road. But you go pretty much anywhere else in Texas, or you go over into New Mexico, and you'll see them dead. Okay? But do you know what armadillos used to look like? That guy. This is called a glyptodon. This is what armadillos looked like a few million years ago. Yeah, well, he was also a lot bigger. That's the size of an SUV. Yeah, they got a little smaller. They also lost the gigantic clubbed tail. They should have kept that? Well, it wasn't evolutionarily positive to do so.
So why aren't they considered like
Dinosaurs
dinosaurs?
came from a group of reptiles. Armadillos are mammals. Yes, okay. So, but can you see the similarities? How this guy came from that guy? You can see there's a little bit of that same sort of armored, like flexible armored texture here around the tail of the glyptodon. You don't have that giant sort of turtle shell looking thing, but you have this right here, this sort of cuff around it. There's an armadillo shell in the next room over. I should have grabbed that for the lecture. Oh well. Okay, so you have a lot of the same characteristics just redistributed according to size. They got smaller over time. The big ones died off. The descendants were able to survive by getting smaller. It was more evolutionary beneficial for them to do so. Okay, sloths. You guys ever seen sloths? They're really cute. Kind of messy, kind of gross. They move really slowly. Why do sloths move slowly? Sloths are real lazy. Do you know that they only go down? They won't even pee in the tree or poop in the tree. They climb down the tree once a week to go relieve themselves on the forest floor. And then they'll climb right back up. It's really funny, actually. But why do they move so slow? It's their metabolism, okay? They have a metabolism that burns real slow. They only eat leaves, okay? They don't get a whole lot of nutrition that leads to a whole lot of energy out of what they eat. So yeah, they move really slow to make up the difference. Do you know what sloths used to look like? Like that. I used to work at a museum where we had a skeleton of one of these, okay? This is called Megatherium. The Megatherium skeleton, when it was sitting on its butt, like so it's up on two legs like it's kind of squatting, the head went floor to ceiling, and the museum had ceilings this high, okay? That's how big sloths used to be. Yeah. This is an animal a saber-toothed tiger would not take on alone, right? And now they climb out of the trees once a week to pee. Because it was evolutionarily positive for them to do so. The big ones, they died off. They couldn't adapt fast enough to the warming climate. And a couple of other things. We'll get to that later.
Is that why a lot of animals aren't so big anymore? Because they couldn't adapt to the warming climate?
What's the problem? Well, this is another thing we're going to get to in a second. What's the problem with having a big body?
More energy.
It takes more energy, which means you need more what? More food. Also, harder to regulate heat. That's why elephants have those big ears that they're constantly flapping to try and regulate the heat out of their bodies. Okay?
They put the blood in the ears.
Yep, they pipe up blood through their ears. They have giant blood veins in their ears, and they're constantly waving their ears back and forth to cool off the blood.
So if like an ear came off, like one of them, it would die.
Yeah, really cruel way to kill an elephant, cut its ears off. Basically die from heat on the inside. It would burn itself alive on the inside. Okay, yeah. But body size requires a lot of energy. Energy comes from food. The more food you eat, the longer you have to eat. You can either eat long or you can change the things you eat. What's the problem? Herbivorous sources of food, like plants, don't have very much energy, but trees also don't fight you, right? Carnivores, they eat meat. They have to chase their prey. They have to expend a lot of energy to get the food that gives them energy, which is why you don't see massive predators anymore. I mean, we've got giant crocodiles and we've got giant great white sharks, right? But we don't have any 40-foot tall T-Rexes anymore, right? We don't have giant Spinosauruses or Giganotosauruses or Carcharodontosauruses or any of these giant predators we've had in the past. Why were they able to survive? Because there was giant herbivorous prey to eat. So these are trends that we see in evolution over time. Sometimes bigger body size is favored. Sometimes smaller is favored. It depends on a vital environmental factor called food quantity, okay? And you see that manifested in the organisms that make up these populations. For example, how large is a herd of elephants? You might have a couple dozen elephants. How large is a herd of gazelle? Hundreds to thousands. Smaller body size. Each individual requires less food. Elephants require more food. The population can only be sustained by the food available. Okay? Okay, so in evolution, there are a couple of different models that we talk about. The Darwinian model, which is called the gradualist model by some, okay? Looks something like this. Here's our L here. Here is time. Here is the number of evolutionary changes that we see over time. The Darwinian model basically states that evolution is constantly going up at about the same rate. Gradualist, slowly over time. Then there's the other one, punctuational. Life stays the same until it can't. Okay? That basically states there are periods where there's no change and then a lot of change. And then no change and then a lot of change. And then no change and then a lot of change. And then no change and then a lot of change. What's the problem with that one? Why? Yes. I mean, it's not like radiation just stops. We're always experiencing radiation causing mutations in the DNA. It doesn't just stop because the environment is stable, right? But by the same token, there are absolutely times when the environment is more stable and fewer mutations will either be positive or negative. And so I personally subscribe to something kind of a mix of both, okay? Where we will have times of less evolution and then more, and then less and then more, and less and then more, and less and then more, based upon external factors. How quickly my environment is changing, and how much radiation my populations are absorbing that cause mutations. Okay? Punctuational equilibrium is one way you can think of that if you'd like. Okay. Now, as these changes are happening, our organisms are slowly deviating further and further apart from each other, getting further and further apart from common ancestry. Did you know that you share approximately 98% of your DNA with a chimpanzee? Bless you. Do you know that you share approximately, 95% of your DNA with a bat? Do you know that you share approximately, gosh, I'm not going to give you a number here because I don't remember. Do you know that you share a lot of your DNA with a tree? Trees have DNA. They are living things on this world. Bacteria. You share a lot of your DNA with bacteria.
Maybe that's why like everything looks the same. Like the I don't know what it's called, but like our neurons and
Oh, are you talking about that pattern?
yeah.
So that's actually a separate thing. The dendritic patterns, like I talked about, like what you see in the shells and the river systems and all that, that probably has more to do with physics. That's probably more of a physics thing, less of a DNA or a ancestry thing. Because otherwise, how would river systems be in all of that, right? How would the patterns we see in pyrolusite? Where's my pyrolusite? Let me show you this. I think this is it over here. Yeah. You look at this, and what do you think? What do you think when you see that? Huh? Yeah, it kind of looks like a brick, but what do you see when you look at that pattern?
I would assume it would be leaves, no?
Yeah, it looks like plant fossil. It's not. This is manganese oxide. It's a mineral called pyrolusite, and it grows naturally in that same dendritic pattern as your brain neurons, as the pattern on those shells, as river systems, as tree leaves. Totally inorganic. So it can't be related to a biological function. It's got to be something at a deeper physics level that we just don't get yet for why this pattern is so prevalent in nature. It's very interesting.
Can I take a picture?
Yeah, sure. Yeah, you can pass it around if you like. Okay, so, but no matter what, living things on our world do go back to a common ancestor. Between us and chimps, between us and bats, between us and turtles, between us and the snake, between us and everything else, go back to a common ancestor at some point. We can see the evidence of this by looking at embryonic development. As embryos develop, either in an egg or in the mother's womb, can't quite tell where she's going. I'm afraid she might fall down here. I think she's fine. Yeah, I was up there. Yeah, that'll work. Thank you. What you'll see is the more basic your embryos are, so as they start growing, they resemble each other very strongly. And then as time goes on, they start developing the traits that are in their DNA that make them the species that they are. And a simple example of this is, do you know that all humans are girls until a very pivotal stage in the development in their mother? The first 4 to 6 weeks of your life in your mother's womb, you were all female. And then a simple chromosome shift occurs at that point, and you'll either start developing male parts or female parts. But everyone starts female. That's a simple example of this, okay? Look at this. Here we have fish, salamander, tortoise, chicken, human. Early embryonic stages, almost exactly the same. Why do we look so much like each other at that stage? Because at that stage, our DNA is almost exactly the same. Like what? Sorry?
Didn't they like debunk some of those vertebrate embryos? Like they said that some of those were like fake or no?
I'm not sure what you're referring to.
Like think about that picture right there. Like didn't they say like that some of those were like fake images? Or, like
Not that I'm aware of. Not that I'm aware of. I could be wrong. I'll look at it later. We can see. It would be worth knowing if that's true. But I can personally vouch, having taken plenty of coursework and this sort of thing that at least some of these are the same. I have seen plenty of reptile embryo. I've seen plenty of human embryo, things like that. And I know that at least some of these do look exactly like that. Okay? Now, the further you get in development, the more deviation you start to see. But there are still some similarities. So this mid-stage embryo, look, my fish and my salamanders, amphibians, still look very similar. They are more closely related to each other than they are to us. Look, the turtle and the chicken look very similar to each other. They are more closely related to each other than they are to these or to us. The further apart we go, the more developed the embryo gets towards the actual species that it represents, the less it looks like the other ones.
People born with like a little tail.
There are people born with tails every now and then. Yeah, this is a product of mutation, right? Basically what happens there is an ancient genetic pathway is reactivated. Genes. Okay. Speaking of which, the study of genetics. We attribute a lot of our understandings of genetics that we have today to this guy named Gregor Mendel. Gregor Mendel experimented with plants for this. Plants are very easy to experiment this sort of thing with. Why? What? They're alive. Sure, they won't fight back. They won't give you a hard time. You can also reliably breed them with each other, right? If I tried breeding two snakes, they may or may not decide to do it. Plants will just do it. There's pollen and then there's flowers and they'll just do it. It'll happen naturally, right? And you have to wait less time between generations. I don't have to wait for an animal to mature to sexual ability. It just needs to, do its thing, right? So a plant it's more reliable to study this way. So he realized that some plants will have different colors of flowers based upon what their parents were, but he couldn't quite figure out how to accurately determine what that would be. So he did an experiment. He took pea plants. Okay? Pea plants grow quickly and they have very distinct, vibrant flower colors. So he took a red flowered pea plant and a white flowered pea plant and he bred them together. What was the result? Red flowers in the next generation. Okay, cool. Where'd the white flower thing go? One of the plants was white flowered. Why are there no white flowers? Instantly raised questions. So then he took that second generation and he bred it with another red flowered pea plant. And you know what he got? Red and white. The only input here was from that first generation white pea plant. He bred this red one with another pure red one and got white flowers out of it, which means that there is something from this parent that made it all the way through here to manifest in that generation. And this is where the concept of genes came from. Okay? That thing, that something that carried from one generation to the next remained dormant and then manifested in a later generation, that took on the name gene. Okay? We call those genes. These are traits which we receive from our parents based upon mutations. Okay? Your eye color, your hair length, how quickly your fingernails grow. These are all parts of your DNA which you have received as part of the coding from your parents' DNA. Okay? Now, we've gotten far enough in our scientific understanding of these concepts that we can map DNA. We can map what we call the genome of an organism, which means that we look at all those billions of lines of coding that go into making an organism what it is over millions of years of evolution. And we know what every single one of those traits controls. And we can flip them on and off. Genetic editing, this is called. It is very cutting edge, very cool, and potentially very dangerous. Why would something like that be dangerous?
Does it have to do with the end product, or would it have to do with what it affects surrounding life? Like, wouldn't it affect the environment in a way that natural selection doesn't take into account, right? Like, it's more or less gene editing.
Yeah, this has nothing to do with environmental change and everything to do with our own choices. This is right. It's dangerously close to that eugenics conversation we had before, right? We've mapped the human genome. We can make our own custom human anytime we want. But here's the kicker, and this is where it comes back to our superhero conversation. We can only turn on things that already exist. So if you ever watch, I don't know, like the X-Men or any of those other things, it's like, he's been genetically modified to have these abilities. He has laser vision, right? Unless you had an ancestor somewhere in the past that had laser vision, sorry, not happening, right? It's not how it works. What this means is we can make past traits manifest. We discovered there's this thing called a Hox gene. The Hox gene is essentially the thing that is the chemical timer in the development of the embryo, right? It will determine, all right, now is the time to start growing fingernails. Now is the time to start growing hair. Now is the time to start growing a nose, right? As you are developing an embryo. It'll turn on, it'll turn off according to the coding in your DNA. We know how to stimulate those things to turn on and off artificially now. And since we now have mapped genomes and we know how to turn things on and off, you can do things like this. This is a chicken in its embryo in an egg. Do you notice anything about this chicken?
What exactly do you need to look at?
The eyes.
Those are pretty typical bird eyes, okay, for that size. Eyes are one of the first things that develops. This is the actual size. Oh, are chickens supposed to have teeth? Do you see the teeth now? Chicken's supposed to have claws? No. Chicken tails aren't even that long either. So what do we have here? This is a chicken that they turned on dinosaur traits for.
Oh, yeah,
We talked about this, and now I'm showing you the picture. This is a chicken dinosaur. This is as close as we can ever get to recreating what the ancestors, what the ancestral avian dinosaurs would have looked like. Now, this is not a velociraptor. We cannot do anything like that. In Jurassic Park, they said, hey, we learned how to modify DNA and add it to things and fill in the holes that were gone using this technique. We can't do that. What we can do is make a chicken of today manifest the same traits as its ancestor did back in the Cretaceous. However long back we want. We can customize a chicken to look as close to its ancestral dinosaurs as we want. We'll never get a Brachiosaurus out of it. We'll never get a T-Rex out of it, but we will have little chicken dinosaurs.
Can you turn on like the height of you, like make them bigger?
However big their ancestors could have gotten, sure. But you can't like turn this into a Goliath chicken dinosaur, right? We are limited only to what is currently in the DNA. Now, people are experimenting with fabricating new biomarkers so that you can make up stuff, but that's not going anywhere as far as I'm aware yet. So you can't give yourself laser vision. You are limited to only making things that exist already in the DNA. So I could technically take a human embryo and modify it so that it had something like sharper teeth, longer teeth, chimpanzee muscles, right? Pick a person up, rip their arms off sort of strength, right? You cannot make a super soldier with laser vision, but you can make one with much, much more strength, okay? And this is where the dangerous part comes in. This is why it's illegal to do this right now. Genetic editing of the human genome is illegal right now because of the potential for taking a living person and making them into a thing. Okay, so this is all very cutting edge, and international law is still working on it. All right, speciation is the word. Oh man, I got to pick up the pace. We're having too much good conversation today. Speciation is what we call it when an organism or a group in a population, okay, starts experiencing these changes in response to an environmental parameter, okay. They begin manifesting these traits that carry through the population to the point where one group of my population will be so different from the rest that we have to start considering them a different species. This is especially true when there's a reproductive barrier. So if I have a group of organisms that look similar to each other in every way but cannot physically reproduce with each other anymore, I have to count them as a different species. Example here, lions and tigers. Do you guys know that a lion and a tiger can actually breed with each other and they can give birth to that? It's called a liger. It's a real animal.
Wait, lion and what?
Lions and tigers can sexually reproduce and have offspring. We call them ligers. So then, why don't we count lions and tigers in the same species?
I'm guessing the ligers
Ligers can't
can't reproduce.
reproduce. The offspring of that must be viable for them to be considered the same species. Otherwise, the species can't continue and it dies off, right? So, ligers are sterile. They cannot reproduce with each other or anything else, and therefore, lions and tigers remain separate species.
Like mules, right?
Mules are another example of this. Mules are when you get a horse and a donkey. They can breed together. They give birth to mules. Mules are sterile. Okay? Okay. When this starts to happen, when one section of your population starts to cause changes in one section of your population as those traits pass onward, and there starts to be that change, that speciation begins, we call it genetic drift. We start seeing genetic drift in places where the organisms slowly start separating from each other because of changes in that environmental parameter, okay? So those are some different things there for you. Speciation and genetic drift. All right, these new species show up when enough of these environmental parameters and enough of that speciation and enough of that genetic drift occurs so that your organisms are occupying not necessarily different niches, but cannot sexually reproduce with each other and look distinct enough from each other that we can tell them apart, in particular as it relates to the fossil record. Okay, that's where a lot of our knowledge of these things comes from. Okay, so an example of this is here we have the island of Palau. Okay, so here's the Philippines. That's the island of Palau. I'm going to erase all of this real quick. Okay, Palau looks like this. Palau is actually an ancient coral reef that became exposed during the last glacial maximum. Sea level dropped, exposing the coral reef above the ocean surface, and it has since gotten overgrown with a whole bunch of plant life. Okay, now sea levels are currently on the rise, right? But the glacial maximum was so recent that it's still pretty much exposed. What happened when that coral reef got exposed was a bunch of the water got caught in these lagoons between the sections of the coral reef, trapping the organisms that were there before, including jellyfish. The jellyfish in the island chain of Palau went from one species that got trapped there when it was a coral reef to each individual lagoon now has a slightly different species of jellyfish. These jellyfish all come from the Palau. Okay, come from Palau. They came from one species and they diverged because the environment in each little lagoon is slightly different from the rest. Some have more sediment, some have less, some have one type of food, some have another, very similar to the Galapagos Islands. Also, the mutations that one population experiences cannot spread to the others. So a beneficial mutation in one population will only stay in that population. It will never mix into the other lagoons because they are separated. They are isolated from each other. Okay? So that's an example of speciation. Some evolutionary trends that are worth mentioning. Evolution in general likes the idea of larger body size. Larger body size, what would larger body size entail? What advantage would that give? Stronger, faster, better, Papa John's. Right? Bad. That was a bad one. Okay, sure. Stronger, maybe faster, although size comes with a downside. You're not usually faster because there's more energy to propel yourself, right? But survivability. It's a heck of a lot harder to take down an 80-ton, 120-foot-long Titanosaur. It's a lot more difficult to take that down than it is to take down something the size of a gazelle or a camel, right? So survivability is absolutely a factor. There's a downside, though. The amount of food you have to eat. Those titanosaurs had to spend the entire day constantly eating. They didn't even have time to chew. They would swallow the leaves and let their stomach do all the chewing. They would swallow rocks. We call them gastroliths. They would swallow rocks down into their stomach to grind up the food as they were walking around, jostling the food in their bellies with the rocks. They didn't have time to chew. They had to keep eating. Okay, so that's one way to live. There's also a limit to how big things can get. Okay? I love using this example. Who likes the Godzilla movies? I'm a sucker when it comes to gigantic creatures fighting each other or robots. Pacific Rim, love Pacific Rim. That's my kind of action. Just thoughtless, really, when you think about it, but real fun to watch. Okay? The Godzilla movies are a good time, but it is literally, physically impossible for anything that big to survive or to exist in the first place. Because, whoop, you good? There we go. Once you reach a certain size, the cross-section of support that your body would need gets exponential, okay? So for Godzilla, now don't judge my Godzilla too much here, okay? Spiky back, spiky back, spiky back, and head, jaws, let's make some arms, okay? Oh man, he has one really long finger, ignore that, okay? And then, okay, here's his legs, his thigh. If we're assuming Godzilla is as big as they have him in the movies, Godzilla's legs would need to be about that big to support the weight of his body. Okay, that looks more like a foot. Woo! Got her. It looks more like a foot, granted. It's supposed to be his leg. Okay? Come here, sweetheart. You're going to hang it up there for a little while longer. You were doing really good. Gravity is pushing down. Yeah, all that mass is going to absolutely shatter any leg bones. Thank you, sweetheart. That was great. She got panicked from the fall and she just pooped all over me. Yeah, so it's going to shatter the leg bones. Don't strike at me. You're the one that fell. Man. Change my shirt in a bit. Stop striking at me. All right. Yeah, so Godzilla, not possible. The animals, like the big monsters in Pacific Rim, not possible, right? Can't happen. So dinosaurs had an upper limit, and it looks like they actually hit that upper limit. Okay, the titanosaurs, those gigantic 120-foot long, 80-ton animals, that's about as big as life can physically get on this world. Now, I say on this world, there are physical parameters that would constrain the size of body on pretty much any world. There are probably worlds out there that exist where larger life could exist, but there are a heck of a lot of worlds where life would have to be smaller by the same token. Okay? There are physical constraints here. Okay. Okay, we already talked about punctuational versus gradual evolution here. An example of this, dinosaurs go extinct. Boo-hoo, they're gone. This leaves open an open niche. Many, many niches that dinosaurs occupied for hundreds of millions of years. What rises to fill those niches? Mammals. They had some competition, right? Birds, crocodiles for a little bit, right? Some larger reptiles tried to fill that niche. But ultimately, mammals filled it. Okay? Mammals took that niche. Most of those niches, I should say. Okay? And it didn't take them that long at all to diversify. Okay? They went from just kind of hanging out as the larger rodent size that they were for most of their time, during the time the dinosaurs were alive, to we had whales and bats within 12 million years of the dinosaurs going extinct. 12 million years. Okay? Did not take long at all. Okay? Okay. By the way, this is kind of an image of the progression of rodents, those sort of rodent-looking animals, towards to whales in that time period. Okay, so are larger rodents that you had, like, say, during the end of the dinosaur time period? I didn't touch anything. That was weird. Okay. All the way down through here, you can see the evolutionary progression to the larger whales. And by the way, whales used to be a lot bigger and a lot meaner than they are today. Okay. Okay. So that takes us to this topic, the subject of evolutionary convergence. You've probably noticed at some point that there are animals that are very similar to each other in body form and function. For example, there are wolves here in North America, and there were at one point Tasmanian wolves over in Australia. They are now extinct. They got wiped out by the farmers and ranchers that were tired of them coming and hunting their flocks, which is unfortunate. Tasmanian wolves were truly beautiful. Look at the similarities here. This one is a marsupial, grew up on a continent that has been separated from North America, where these were, for more than 100 million years. Separated since they were their ancestors were essentially rodents. Okay? And yet, look at the similarities. Evolution encouraged the same type of traits that were positive for both populations on totally different continents. Same thing for the flying phalanger, which is a marsupial, and the flying squirrel in North America. Then you have the marsupial anteater and the anteater. The marsupial mole and the mole. This is convergent evolution. Evolution favors the same traits in different populations. And so we get different mutations, sure, leading to the same pattern. Okay? Example of this, the niche that is today occupied by dolphins used to be occupied by reptilian ichthyosaurs, which before was occupied by placoderm fish. Looking very similar to each other because they filled the same niches. Now, extinctions man, that poop really went everywhere. I'll try and pick some of that up with a sponge later. Those niches, extinctions, we're talking about extinctions now, are relatively recent development in scientific history, okay? Because for a long time, the major religions refused to believe that there was any permanent death of anything on this world that was made by God, okay? We now know things go extinct all the time. Things go extinct every day now. Anything can cause these. Any environmental parameter, okay? Changes in environment, like your temperature, acidification of the ocean, things like that. These days, overhunting, right? We see these extinctions through time. If you look at this, you'll see this is the number of genera, which is the plural of genus. Remember, we have genus and species as part of our taxonomy. That's the number of genera that we know about in the fossil record. And you can see how it goes up and then it goes down. Every time it goes down like that, that's an extinction. Up and down. That's the end-Triassic extinction. Then we have a couple of extinctions during the Jurassic, and then whoop, a major extinction at the end of the Jurassic. Then we have a couple of, oh, look at that big spike right there, and then an extinction, then a spike, and then way down here at the end of the Cretaceous. What was that? That was the extinction that killed the dinosaurs, okay? So we can track these through time by seeing the number of things like genera, the different types of organisms that are in the fossil record. Sometimes it can be fooling us, though. Whenever we see an example of speciation occur, where the original population is no longer in the fossil record, because a new population has filled that same niche, like the original population just changed, it didn't die off, it just changed over time, that can sometimes look like an extinction. So we have to pay careful attention to what is the driving force that we can see in the fossil record behind these changes. If we can find not an offspring, but like a subsequent species that came from the original, then that's sometimes called a false extinction, okay? And then finally, there are these things called mass extinctions, where we lose entire orders. Remember, so we've got species, genus. Then we go up a little bit, right? There's things like family, yada, yada. And then there are orders up there. When we lose entire orders of organisms, that's a substantial amount of things that are dying off. That's what we call a mass extinction, okay? We are actually in the middle of a mass extinction right now. We are losing entire orders of living things on our world. Now, after an extinction, what is left behind? Bingo. Empty living space. You guys remember that commercial? Free real estate. No? You don't remember that? The creepy real estate guy? No? Okay. Old references, I know. Let the jokes fly. Okay. Yeah, there's a lot of empty living space, and what's going to rise to fill it? The survivors. So you'll notice that there's always a major extinction and then a massive increase in the amount of life. We call that increase of life a radiation. No, it's not radiation like flying particles that cause mutation. Different context of the word radiation. Okay? It's this type of radiation. Are you going to drop off of me again? Silly girl. All right. Come here, you. All right, yeah, that's fine. You just hold on with your tail. Radiation in the term of expansion, okay? Radiating from a central source outward is this type of radiation I'm talking about now. So after every extinction, there is always a radiation of organisms diversifying to fill the niches left vacant by what went extinct. Okay, so that's what I'm talking about there. Any questions? Okay, well then let's move from here on to preparing for our Exam 2 review. We have, man, this went long. We had so many good things to talk about today, this lecture is usually like half the size of my other ones. It's only 16 slides. We went really long today. What do you want to talk about? What questions do you have for Exam 2? Exam 2 is covering, by the way, Module 2, which is lectures 5, 6, 7, and 8. Okay? So talk about like the diversity of life, correlation of the fossil record, everything we talked about today, things like that. Stratigraphy, okay, that's a big part of it. Your exam is going to be 20 questions. All the usual type of questions, including short answers, will be on there.
Will we have to look at the stratigraphy graphs?
There very well might be sections of stratigraphy to look at and interpret, yes, because that was something we discussed in class during this lecture. Yeah. What else?
What about, is there anything we need to define? Like what are the terms that you've given this class that?
I mean, we've talked about a few. We've talked about, just today alone, we've talked about extinction, we've talked about speciation, we've talked about...
Is there any like that we need to have like the exact definition? Or
exact definition? I gave you a few approximate definitions, but nothing that I would necessarily say, it's this or nothing, right? Like the principle of uniformitarianism, I need you to know word for word. I need you to know things like the definition of a mineral, because there are so many definitions out there, and we're working off of the one that I personally teach, right? There's nothing really like that here. Everything I've taught you can be approximated and be correct. Okay, give me your best understanding of it, and as long as it's coherent and close to what I taught you, I'll know what you're talking about. I just need to know that you grasp it, not necessarily that you memorized it. Good question. I smell like snake poop all day. What else? Oh, like in the lab?
No, well,
What do you mean?
like how we did in lecture 6, we were talking about like for the
The lifespan. Oh yeah, like in the lab where you had to put X's in every square that thing was alive.
I don't know. But do we have to do something?
I mean, no. Anything that I test specifically in a lab is not necessarily going to be. I mean, it might be in the exam. It's fair game, but I prioritize what we talk about in lecture. Okay.
Are we getting that first?
No, because we kind of went long, and I'm giving you the exam 2 review right now. We won't be doing lab 4 today. That gives you a little more time to catch up on your other labs and prepare for this exam. Okay. Other questions? Bottle down. Someone call IXII. It's a Roman numeral joke. Yeah, it's 911 in Roman numerals. IXII. Yeah? Yeah? Yeah, you're going to use that one now, aren't you? You're going to forget it. Niche joke.
A niche joke?
Some bottles just don't want to stand up, brother. All right. What else you got for me? Anything we've talked about over the last 2 weeks that you just don't get? Go through your notes. Think about it. I'm gonna get some paper towels to clean up the rest of this poop.
Are we gonna have to read into like the Eon era periods?
It would be very good idea to remember what eons, eras, periods, and epochs are, and maybe even what the major ones were. Now, you can write that down. Like in all of my other exams, you can use your notes here. So it might be worth it to have, just like make a quick sketch of what the geologic timescale looks like. So crazy to think that this white and green pasty stuff used to be a rat.
So small compared to
Yeah, I mean, they process extremely efficiently, which is why they are able to eat only once every couple of weeks if they have to. I'm feeding her once a week right now because I'm trying to help her get bigger faster.
Also, you're overfeeding her.
I'm not overfeeding her. I'm just feeding her more than she probably would necessarily need in the wild.
Dang, it is still once a week.
Wow, that was a lot of hand sanitizer. Yeah, once a week is more than she would typically need or get in the wild. I've had that hand sanitizer over there since COVID, and it has more the consistency of soap than anything now. It's kind of gross. All right, sweetheart. Any other thoughts or questions? I'll, in 3 minutes, if no one else has any other thoughts or questions, I'll go ahead and end this recording and open up the exam. The guys? Oh, like the fathers of science and stuff like that? Good idea to remember why I brought them up and what contributions they made. Yeah? I brought them up for a reason, right? All right, that should be sanitary enough. All All right, I'm going to go put her back in her terrarium. I will be right back. Probably take off my microphone first. I am still recording because I wanted to make sure that my online students get the answers to any questions you guys have about the exam. So I'll be right back. I'm just, in like 20 seconds, I'm just going to put her away, and then I'll answer any other questions you have. And in a minute or two, I'll end the recording if there are no other questions. Okay, I will be right back.
Actually, you did
I still go ahead.
Big clothes gotta go, dude. Yeah. I was trying to go in my head. Did you guys need to do the same like this type of thing?
Are you so angry?
What do you do?
All right. Thought of any other questions before I end this thing? You're all real confident? Concepts of evolution, mutation, adaptation. Think you're ready to take that down? Yeah? All right. Good deal. Well, I will end the recording here and open the exam.